Hello, my name is Kai and welcome to the Theoretical YouTube channel, where the holidays are our favorite time of year. There's just so much great stuff, from the people laughing and having a good time with their families, to the non-stop Christmas soundtrack that seems to just keep playing and score your entire life for like a month. It is very difficult to find something about the holiday season that's that bad. It's not even like we're sacrificing anyone for our own well-being. It's literally the season of giving. The better off we are, the better off the world is. It's all just so great. But you know what and I'm willing to bet plenty of you, have wondered about the holidays? Christmas in particular? What's the deal with Santa Claus? I mean, he used to be a cool saint guy that would throw money into the children's windows to keep them from selling their bodies to creepy old guys. True story. Look it up. No, don't look it up. But apparently in the last century he got like a brand deal with Coca-Cola, and now he flies around the entire world in one day delivering presents to children who are nice. And if they're naughty, he gives them coal. But like, what the heck? If they end up burning their house down, they better not get put on the naughty list again, because you're the one who decided to give them literal fire to play with. And as a thanks for him breaking into our home, we leave out a plate of cookies for him to eat on his way. And that's a lot of calories. But exactly how many calories? Well, today we're going to find out. Okay, it's not actually that difficult to find out how many calories Santa consumes on Christmas Eve. All we have to do is find out how many cookies he eats and how many calories each of them has. So how many cookies does Santa eat on his 24-hour voyage around the world? Well, there are about 2.18 Christians in the world, but to be conservative and make my math a bit easier, I'm just gonna estimate that there are 2 billion people who celebrate Christmas around the world. Now, the average household has about 2.6 people in it. However, that's brought down a lot by people living alone, so the average family has about 3.8 people living in it. So if we divide 2 billion by 3.8, we get 562,315,789 houses that Santa has to visit. So now I'm going to round down again, both for my sanity and to keep a conservative estimate. We can justify this by saying maybe 26 million families don't actually leave cookies out for Santa. And for now, we will also say that he only eats 1 cookie from each plate. Okay, so now we know that Santa eats about 500 million cookies each Christmas Eve. But how many calories is that? Well, how many calories are in an average cookie? Looking at recipes for some of the most popular cookies around the Christmas time, we can see what the average calorie count is. Now from that data, we can find the mean to be about 120 calories. And after all that, we can count how many calories Santa eats in one day. If we take our number of cookies and multiply it by our average calorie count, we get that Santa eats 60 trillion calories in one day. And hold on, we're nowhere close to being done here. Sure, that's a big number, but like, who even knows what a calorie is? It's technically the amount of energy needed to raise 1 gram of water 1 degree Celsius, but we've also been using food calories, which just, swap out the gram of water for a kilogram of water. But what is a calorie? I mean, sure, I guess now we know that if you burned Santa, he could raise 60 trillion kilograms of water 1 degree Celsius. But that's still just some weird abstract idea. However, if you convert the calories to joules, we can compare it to a lot of other things. There are 4,184 joules in every calorie, making the total amount of energy that Santa consumes 251 trillion joules. This is not only enough to power the entire city of London, but the entire London area for 6 hours. Santa could power the Saturn V rocket for 7,276 kilometers. It only had to go to space, which is just 60 kilometers in the air. This could do that 90 times. A normal 2,000 calorie a day diet would take 82,192 years to add up to that amount. You'd have to literally be as old as language to eat that much. But Santa does it in one day, every single year. Alright, that's all well and good, but who even cares if Santa can power the Saturn V rocket or eat half of human existence? Sure, these are huge numbers, but they don't really have anything to do with Santa. What I want to know is whether Santa can use this energy to do what he does best: fly around the world delivering presents to kids on Christmas. So to find out if Santa has enough energy to travel around the world, all we need to know is one of the most crucial concepts in all of physics: work. Well, actually we need to know a few things to calculate out work, so it's not that easy. Work is used in physics very similarly to how it's used in everyday language. Work is the amount of energy needed to exert a force, so clearly one of the components is the force itself, but the other might not be so obvious. Think about this. If you had a 1 kilogram weight dangling above your hand, which would have more energy when it hit your hand, i.e. which would hurt more, if it fell from 1 meter or 1 centimeter? The force exerted on the object isn't changing. It will always be the acceleration due to gravity, 9.8 meters per second, times the mass of the weight, 1 kilogram, so 9.8 newtons. So what's changing? Well, the distance it's falling, and that's exactly why the equation for work is force times distance. In the case of the weight falling from the centimeter, the energy is 0.098 joules, while the weight falling from a meter has 9.8 joules, all of which goes into deforming your hand. So since work is measured in joules, all we need to do is find the number of joules that it takes to move Santa's sleigh around the world, and then compare that to the number of joules that Santa eats in cookies. So to find work, we need the amount of force it takes to move the sleigh and how far Santa has to travel. Let's start with the distance, since that's the harder part. To find the distance Santa has to go around the world, first we need to find his route, which is very difficult. So difficult, in fact, that the Clay Mathematics Institute is awarding $1 million to anyone who can figure it out. Well, not exactly. In the year 2000, the Clay Mathematics Institute issued out their 7 Millennium Problems. These were the problems that they deemed the most important for mathematics, and they're willing to pay $1 million for a solution to any of the problems. So far, only one has been solved, and the guy declined the money. But one of the unsolved problems is P versus NP, which deals with calculations that even our fastest computers can't do in a reasonable amount of time, such as calculating the absolute quickest route Santa could take around the world. But we can get close. Let me explain. So if Santa's going around the world delivering presents to each Christmas celebrating house, he needs a path that touches each house once. And if he wants to go back home in the end, he's going to want the North Pole to be the first and last stop. But how many possible paths could he take? Well, let me introduce you to the wonderful world of graphs. No, not those kinds of graphs. Those kinds of graphs. What you would normally think of as a graph, you know, like the Cartesian plane with some sort of curve on it that you have to find the derivative or something, is actually called a plot in mathematics. This is so as to not confuse them with what they actually call graphs. In math, graphs are just a bunch of points that may or may not be connected by lines. Wow, that was a really bad explanation. A graph is basically just something like this. And every graph has a bunch of things called Hamiltonian cycles, which is one line that connects every single point on the graph and then leads back to the beginning. So now all we have to do is find the shortest Hamiltonian cycle for his trip. But how many are there? Well, what about the Hamiltonian cycles for just a square? Well, instead of a square, let's imagine that we just had 4 dots in a row with a single line connecting them and one line leading back to the beginning. So now the number of Hamiltonian cycles is just the number of ways we can rearrange these dots, excluding the beginning dot, since that one can't be in the middle because we have to go back to the beginning in the end. And then we can divide that number by 2, since half of the cycles are just going to be mirror images of each other, which gives us this equation, n being the number of points that you have to touch. So for a square, there are 3 distinct paths you can take to touch all the points. But the thing is, Santa has to make 500 million stops. Subtracting 1 and taking the factorial, even after dividing by 2, is an unfathomable number. And this is why we can't know the absolute best route, because we literally can't check all of them in 10,000 years with our fastest computers. However, if you condense the graph into fewer points based on population density of Christians, it gets a lot easier. And thankfully we don't even have to do all that, because it was already done partly by the North American Aerospace Defense Command, and then Ben Blatt improved on that design. Blatt's route decreased NORADs from 178,899 to 158,929 miles. Okay, so now we have our distance, but what is the force that needs to be applied to move Santa's sleigh? Well, we could use Newton's handy-dandy second law that says that force equals mass times acceleration, getting the acceleration from the time he has and the distance he has to travel, and getting the mass from the data that NORAD has actually collected on the weight of the sleigh itself. His acceleration would have to be about 0.068 meters per second squared, and NORAD has said that the weight of his sleigh is about 75,000 gumdrops, or using the average weight of a gumdrop we can get that it's about 57.75 kilograms, which is really light, so apparently Santa knew that decreasing the weight of his sleigh would actually decrease the amount of energy he needed to go around the world. However, his mass times his acceleration is not the only force he needs to overcome. More important is the force of drag. Clearly, while Santa optimized his sleigh for weight, he did not do the same for aerodynamics. In a study done by Chris Beeves in an article called Simulation for an Aerodynamic Sleigh, he found that the drag coefficient of Santa's sleigh is about 1.32. So using that coefficient, the density of the air at cruising altitude, the velocity he'd have to be going, and the area of the face of his sleigh, again using NORAD's specs, we get that the force he would need to overcome drag is over 40 million newtons. So if we plug that into our equation that says that the total force minus the force of drag is equal to mass times acceleration, we get that the total force is 40,491,873.6 newtons. And if we multiply that by the distance Santa would need to travel, we get that he would need, and I am not memorizing this one, 10,624,624,524,624,995 joules of energy. Which means that the amount of energy Santa gets from cookies is not enough. He would need about 40 times the amount of energy he already gets. However, we were being extremely conservative in all of our estimates, and we didn't even count the milk that he drinks with every cookie. And we were only talking about the tradition of leaving cookies out for Santa. But what about mince pies or brandy? Those are even higher in calories. But most importantly, this whole time we've been leaving out the reindeer whose job is to pull the sled. Leave them some carrots, will ya? Or better yet, let them drink brandy too. But if we're just talking about cookies and carrots, then either Santa could eat 38 cookies at each house, every reindeer could eat 22 carrots at each house, or somewhere in between. Literally anywhere on this line would do. So could Santa really fly around the world using only the energy he gets from cookies? Sure, I think it's plausible, but that's for you to decide. You're the one who leaves the cookies out for him. And who knows, maybe that last little bit of energy he needs is pure Christmas spirit. So do Santa a favor and leave out some extra cookies this year. It may help him in more than one way. Okay, so it looks like that's all we have for today. We've actually been planning this video for a while, but it seems like every Christmas season it kind of comes and goes before we even get around to starting this video. So I'm really glad we did the math and made it a thing this year. Clearly you like this sort of stuff because you somehow made it through all of those numbers to the end of this video, so why don't you go down there and hit the subscribe button, maybe give this video a like. If the comment section is down there, then you could ask a question, leave a comment, but COPPA literally happens in 5 days, so we don't know how that's gonna work out. But if there is no comment section and you really want to interact with us, why don't you go over to Theory_Central on Twitter, because that is literally the only place you can interact with us. Because COPPA. On the bright side, we don't have very many followers, so anything you tell us, I guarantee we will read. But that's it for today, so until next time, thanks for watching, and we'll see you later.
Grandpa's gonna sew the pants off for Santa.